Welcome! Today, we'll be exploring LeetCode problem number 1712, ways to split array into 3 subarrays. This is an intriguing problem that challenges your understanding of arrays and algorithmic efficiency. Let's dive in and break it down step by step. In this problem, you are given a sorted integer array called nums, and your task is to determine the total number of ways to split this array into 3 non-empty, contiguous subarrays. These subarrays are referred to as the left, middle, and right subarrays. The key condition here is that the sum of the elements in the left subarray must be less than or equal to the sum of the elements in the middle subarray, and the sum of the middle subarray must be less than or equal to the sum of the right subarray. Formally, this means splitting the array into 3 sections, nums, 0, I, for the left, nums, I, j, for the middle, and nums, j, n, for the right, where I and j are indices satisfying 0, I less than j less than n. The task is to count all such valid splits where the 2 conditions on the subarray sums are satisfied. The input to the problem is a sorted array nums in non-decreasing order, meaning the elements are arranged from smallest to largest. The output is a single integer that represents the total number of valid ways to split the array into 3 parts as described earlier. For example, in the case where nums is 1, 1, 1, there is only one valid way to split the array. This is because there's only one arrangement of the subarrays that satisfies the sum conditions. The explanation for this example will help clarify how the sums are evaluated. In this example, the array nums is split into 3 subarrays. The left subarray is 1, the middle subarray is 1, and the right subarray is 1. The sum of the elements in each subarray is 1. Now, if we check the conditions, the sum of the left subarray, which is 1, is less than or equal to the sum of the middle subarray, which is also 1. Similarly, the sum of the middle subarray is less than or equal to the sum of the right subarray, which is again 1. Since both conditions are satisfied, this arrangement is valid, and there is exactly one valid way to split this array. Another example is when nums is 1, 2, 2, 2, 5, 0. Here, there are 3 valid ways to split the array, and we will examine those next. For the array 1, 2, 2, 2, 5, 0, the 3 valid splits are as follows. In the first split, the left subarray is 1, the middle subarray is 2, 2, and the right subarray is 2, 5, 0. Their sums are 1, 4, and 7, which satisfy the conditions 1 equals 4 and 4 equals 7. In the second split, the left subarray remains 1, but the middle subarray extends to 2, 2, 2, and the right subarray is 5, 0. The sums here are 1, 6, and 5, satisfying 1 equals 6 and 6 equals 5. Finally, in the third split, the left subarray is 1, 2, the middle subarray is 2, 2, and the right subarray is 5, 0. The sums are 3, 4, and 5, which meet the conditions 3 equals 4 and 4 equals 5. This gives a total of 3 valid ways to split the array. However, in cases like 3, 2, 1, no valid splits exist because the conditions cannot be satisfied. The problem comes with specific constraints that you must adhere to. The array length is guaranteed to be between 3 and 100,000, making it essential to have an efficient solution. Each element in nums is a non-negative integer and can go up to 10,000. Additionally, the array is sorted in non-decreasing order, which is a key property that can be leveraged to optimize the solution. Some edge cases to consider include arrays of the minimum length of 3, where there's only one possible split, or arrays with all elements equal, like 0, 0, 0, 0, which allow multiple valid splits. On the other hand, arrays like 3, 2, 1 have no valid splits because the left subarray's sum would always exceed the other subarrays. Finally, large arrays near the maximum size will require efficient algorithms to ensure the solution runs within time limits. To solve the problem of splitting the array into 3 subarrays while meeting the condition that the sum of the left subarray is less than or equal to the sum of the middle subarray, which in turn is less than or equal to the sum of the right subarray, we start by considering a brute force approach. In this method, we analyze all possible ways to split the array by iterating over every pair of split points. The first loop identifies the split index where the left subarray ends, and the second loop determines where the middle subarray ends. For each pair of split points, we calculate the sums of the left, middle, and right subarrays and validate the condition. While this approach is intuitive and straightforward to implement, it involves repeatedly calculating subarray sums for every possible combination, leading to a time complexity of O(n)^3. This makes it highly inefficient for larger arrays due to redundant computations, and we must look for a more optimal solution. The inefficiency of the brute force approach arises from the repeated calculation of subarray sums. To address this, we can use an optimized strategy that combines a prefix sum array and a two-pointer technique. The prefix sum array allows us to compute subarray sums in constant time by pre-computing the cumulative sums of the elements. Once the prefix sums are prepared, we iterate through the array to determine the first split index, ensuring the left subarray is non-empty. For each valid first split index, we use two pointers to identify the range of valid indices for the middle subarray. The lower pointer finds the smallest index where the sum of the left subarray is less than or equal to the middle subarray, while the upper pointer identifies the largest index where the sum of the middle subarray is less than or equal to the right subarray. The difference between these two pointers gives us the count of valid splits for that specific first split index. By eliminating redundant calculations and leveraging the two-pointer technique, this method achieves a time complexity of O(n), making it significantly more efficient than the brute force approach. The chosen strategy for this problem is the two-pointer approach combined with the prefix sum array. This method is optimal because it reduces the time complexity from O(n) cubed to O(n), while maintaining clarity and correctness. The key to its efficiency lies in a few critical observations. First, the prefix sum array allows subarray sums to be calculated in constant time, which eliminates redundant sum computations. Second, the two-pointer technique works seamlessly with the sorted nature of the prefix sums to quickly locate valid indices for the middle subarray, ensuring that we only focus on feasible splits. Finally, the monotonic nature of the sum conditions ensures that as we move the pointers, the constraints are naturally preserved. These insights together create an efficient and elegant solution, making this approach the clear choice for tackling the problem. The two-pointer method stands out as the most efficient and effective approach for solving this problem. By minimizing unnecessary computations and leveraging the prefix sum array, it achieves a balance between clarity, maintainability, and optimal performance. While the brute force approach is simpler to implement, it is impractical for larger inputs due to its cubic time complexity. In contrast, the two-pointer strategy not only improves performance but also handles the problem's constraints in a structured and logical manner. This does require additional effort in terms of implementation, such as managing the prefix sum array and coordinating the movement of the two pointers, but the trade-off is well worth the efficiency gained. Overall, this approach is the best choice for solving the problem in a way that is both scalable and robust. The problem requires us to split an array into three non-empty contiguous subarrays while satisfying two key conditions. First, the sum of the left subarray must be less than or equal to the sum of the middle subarray. Second, the sum of the middle subarray must be less than or equal to the sum of the right subarray. This means we are not just splitting the array, but also ensuring these specific relationships between the sums of the subarrays. Given the constraints, where the array can have up to 100,000 elements and each element can be as large as 10,000, we need an efficient approach to solve the problem. Brute force methods would be too slow, so we must rely on optimized strategies to handle these constraints effectively. To solve the problem efficiently, the first step is to pre-compute the prefix sum array. The prefix sum array allows us to calculate the sum of any subarray in constant time. Specifically, prefix I stores the cumulative sum of the first I elements of the array. This means that if we want to find the sum of a subarray between indices I and j, we can simply use the formula prefix j, prefix I1. By pre-computing the prefix sums, we avoid repeatedly summing over subarrays, which would take linear time for each query. The formula to compute the prefix sum is straightforward: prefix I equals prefix I1 plus nums I, and it initializes with the first element of the array. Once the prefix sums are ready, we can efficiently calculate subarray sums as we iterate through potential endpoints for the left subarray. The next step is to loop through all possible endpoints I for the left subarray, ensuring that it is non-empty by starting the loop where I equals 1. After determining the endpoint of the left subarray, the focus shifts to efficiently identifying the range of valid middle subarrays. The task is to find the smallest j, which marks the start of the middle subarray, such that the sum of the left subarray is less than or equal to the sum of the middle subarray. Mathematically, this translates to checking if prefix j, prefix I1, is greater than or equal to prefix I1. To find this j efficiently, we use binary search, which allows us to pinpoint the exact starting index in logarithmic time. Similarly, we need to find the largest k, which marks the end of the middle subarray, such that the sum of the middle subarray is less than or equal to the sum of the right subarray. This involves another binary search to ensure prefix k, prefix I1, is less than or equal to prefix n1, prefix k. With these two binary searches, we establish the range j, k, for valid middle subarrays, and the number of valid splits for this I is simply k, j plus 1. There are several important insights into why this approach is efficient. First, binary search is a critical tool here. By leveraging binary search, we avoid the naive approach of testing every possible split, which would take cubic time. Instead, binary search allows us to find the valid range of indices for j and k in logarithmic time. Second, managing the constraints is crucial. We ensure that all subarrays are non-empty by keeping the relationships I less than j and j less than k intact. The prefix sum array is instrumental here, as it enforces these conditions efficiently. Lastly, we account for edge cases such as arrays with the minimum size of 3, arrays with uniform values where every element is the same, and arrays with very large values. These edge cases help us validate the robustness of the algorithm under different scenarios. The solution relies on two key data structures, the prefix sum array and binary search tools. The prefix sum array allows us to calculate subarray sums in constant time, while binary search helps efficiently determine the boundaries for valid middle subarrays. Together, these structures enable the algorithm to run in n log n time. Specifically, computing the prefix sums takes n, iterating through all possible endpoints for the left subarray takes n, and performing binary searches for each endpoint adds a logarithmic factor, resulting in a total time complexity of n log n. The space complexity is n, due to the prefix sum array. This balance of time and space efficiency makes the approach well suited for the given constraints, enabling it to handle large input sizes effectively. This solution efficiently calculates the number of ways to split an array into 3 subarrays that satisfy the given constraints. Step-by-step explanation. 1. Prefix sum computation. The prefix sum array is computed to allow 1 range sum queries. This is a common optimization in problems involving subarray sums. 2. Iterating through split points. We iterate through the array, where I marks the end of the leftmost subarray. This ensures that the left subarray is non-empty. 3. Binary search for valid middle subarray. The problem requires sum left equals sum middle. Using the prefix sum, we find the smallest valid starting index j for the middle subarray using bisect_left. Similarly, we need sum middle equals sum right. The largest valid end index k for the middle subarray is found using bisect_right. 4. Counting valid splits. For each valid I, the number of valid splits is the range j, k, which is added to the total count. 5. Returning the result. Finally, the total number of ways is returned. Why is this efficient? The prefix sum array allows 1 range sum queries. Binary search operations are log n, and they are performed for each possible I, resulting in n log n complexity. Edge case handling. The algorithm ensures that all subarrays are non-empty by limiting the ranges of I, j, and k. Arrays with fewer than 3 elements naturally return 0, as there are no valid splits. This solution is optimal for the given constraints of 1 equals nums.length equals 10 to the power of 5. Here, we begin by importing the necessary Java utilities and defining our solution class. The main method we're focusing on is called ways2split, which takes an integer array called nums as input. First, we calculate the length of the array and initialize a prefix sum array that will help us efficiently compute the sums of subarrays. The prefix sum array is one element larger than the input array to accommodate the cumulative sums. Next, we compute the prefix sums by iterating through the nums array. For each element, we add its value to the cumulative total from the previous step. This allows us to quickly query the sum of any subarray later. After that, we initialize a variable total ways to keep track of the number of valid splits we find. The core of the solution lies in iterating through the array using a variable I, which marks the end of the left subarray. For each position of I, we calculate the sum of the left subarray using the prefix sum array. Then, we use binary search to identify the range of indices j that can serve as the start or end of the middle subarray, ensuring that the split conditions are satisfied. Specifically, we call two helper methods, binary search left to find the smallest valid j and binary search right to find the largest valid j. Finally, if the range defined by j and k is valid, we calculate the number of splits for this configuration and add it to total ways. Once the loop override completes, we return the total ways variable, which now contains the total number of valid splits for the given input array. To support the binary search operations, we define two helper methods. The first one, binary search left, helps us find the smallest index j for the middle subarray such that the sum of the left subarray is less than or equal to the middle subarray's sum. This method takes the prefix sum array, a target value, and the low and high bounds for the search. Inside the method, we use a standard binary search approach. We maintain a window between L and R and calculate the midpoint mid. If the prefix sum at mid is less than the target, it means we need to move the left boundary up, so we set L to mid plus 1. Otherwise, we move the right boundary down to mid. This process continues until L equals R, at which point we return L as the smallest valid index. Similarly, we define the binary search right method, which helps us find the largest index j where the sum of the middle subarray is less than or equal to the right subarray. This method also uses the prefix sum array, a target value, and the low and high bounds for the search. The logic is similar to the binary search left method, but the key difference lies in the condition for adjusting the boundaries. In the binary search right method, we continue the binary search by checking if the prefix sum at mid is less than or equal to the target. If it is, we move the left boundary up by setting L to mid plus 1. Otherwise, we move the right boundary down to mid. This ensures that, by the time the loop ends, the variable L will point to the smallest index that exceeds the target. To get the largest valid index for the middle subarray, we return L minus 1. By combining these binary search methods with our main iteration logic, we efficiently find all valid ways to split the input array into 3 subarrays that satisfy the problem's conditions. This approach leverages the prefix sums for constant time subarray sum calculations and binary search for logarithmic time index lookups, resulting in a solution that is optimal and scalable even for large input arrays. This completes the Java implementation for the problem. To solve this problem, we start by computing the prefix sums array. The prefix sums represent the cumulative sum of the array up to each index. For the given array nums equals 1, 2, 2, 2, 5, 0, the prefix sums are calculated step by step. At index 0, the value is 0. At index 1, the sum is 1. By adding 2 at index 2, the cumulative sum becomes 3. This process continues until the final value, which results in the prefix sums array 0, 1, 3, 5, 7, 12, 12. Once we have the prefix sums, we iterate through the array, treating I as the endpoint for the left subarray. The iteration runs from index 1 to n2, since we need to leave room for middle and right subarrays. This sets the stage for identifying valid ranges for splitting the array. When I is 1, the left subarray sum is prefix underscore sum, 1 equals 1. To find valid ranges for the middle subarray, we use binary search. The goal is to determine indices j and k, where j is the start of the middle subarray, and k is the endpoint of the middle subarray. Using bisect underscore left, we locate the smallest index j where the middle subarray sum is at least as large as the left subarray's sum. Similarly, with bisect underscore right, we locate the largest index k that keeps the sum of the middle and right subarrays balanced. For I equals 1, j is found to be 2, and k is 4, giving a valid range of 2, 3. This range contributes k, j equals 2 to the total number of ways. Next, for I equals 2, the left subarray sum is 3. Using the same binary search approach, we find j equals 3 and k equals 4, giving a valid range of 3, 3. This contributes an additional 1 to the total. So far, the total number of ways is 2 plus 1 equals 3. For I equals 3, the left subarray sum is prefix underscore sum, 3, equals 5. Here, binary search fails to find a valid range because the condition j equals k is not satisfied. This means no valid splits exist for this iteration, and we add 0 to the total. Now, let's consider a simpler example, nums equals 1, 1, 1. The prefix sums for this array are 0, 1, 2, 3. Using the same method, for I equals 1, the left subarray sum is prefix underscore sum, 1 equals 1. Binary search gives j equals 2 and k equals 3, resulting in one valid range, 2, 2. This contributes j equals 1 to the total number of ways. In this example, the total number of ways is just 1. The key to solving this problem efficiently lies in the use of binary search. By leveraging bisect underscore left and bisect underscore right, we can quickly identify the valid ranges for j and k that satisfy the conditions for splitting the array. For example 1, the total number of ways to split the array is 3, while for example 2, it is 1. This method ensures that we achieve the solution in an efficient manner, even for larger input sizes. Here, we break down the time complexity of the solution step by step. First, the prefix sum array is computed in a single pass over the input array, nums. This operation takes n time because we are simply iterating through the array once and calculating cumulative sums. The advantage of this step is that it allows us to compute the sum of any subarray in constant time, 1, which is a key optimization. Next, we have the outer loop, which runs from I equals 1 to I equals n 2. This means the loop iterates n times. Within each iteration, the algorithm uses two binary searches to determine the valid ranges for the middle subarray. These binary searches are performed using the bisect underscore left and bisect underscore right functions on the prefix underscore sum array. Since the size of the prefix underscore sum array is n, each binary search takes log n time. Therefore, for every iteration of the outer loop, the total cost of the two binary searches is log n. When we combine these operations, the total time complexity is derived as follows. First, we have n for computing the prefix sum array. Then, for the outer loop, there are n iterations, and during each iteration, the binary searches together contribute log n. Multiplying these gives us n asterisk log n, which is n log n. Adding the prefix sum computation to this, the overall time complexity remains n log n, as it dominates. Now, considering the space complexity, we start with the input array nums, which already requires n space. Then, the prefix sum array is created, and it also has a size of n, as it stores cumulative sums for each index up to n plus 1. Apart from these, the algorithm uses only a few scalar variables like total underscore ways, left underscore sum, j, and k, which require constant space, 1. Since no other data structures are used in the solution and there is no recursion or stack overhead, the overall space complexity is n, primarily due to the prefix sum array. Now, let's analyze the time complexity across different scenarios. In the best-case scenario, the binary searches quickly find valid ranges for the middle subarray, perhaps with minimal iterations. However, since the outer loop and binary searches still dominate the process, the asymptotic complexity remains n log n. For the average and worst-case scenarios, the algorithm performs the same steps, computing the prefix sum, iterating through the outer loop, and conducting binary searches in each iteration. The work done per iteration is consistent, so the time complexity for these cases also remains n log n. Therefore, the time complexity is n log n across all cases, while the space complexity is n. To understand the efficiency of this solution, let's compare it to a brute force approach. A naive solution would involve iterating over all possible split points, I, j, and k, to check the conditions for valid splits. This would require 3 nested loops, leading to a time complexity of n cubed. Such an approach is computationally expensive for large input sizes. In contrast, the optimized solution leverages the prefix sum array and binary search, significantly reducing the complexity to n log n. The key insight here is the monotonic property of the prefix sums. This property allows us to use binary search to efficiently determine the valid ranges for j and k, rather than iterating through all possibilities. This optimization drastically limits the search space and makes the solution far more scalable. The overall time complexity can also be proven mathematically. Let's denote the size of the input array as n. First, the prefix sum computation involves a single pass over the array, contributing n. Next, the outer loop iterates n times, and within each iteration, 2 binary searches are performed, each taking O log n. Combining these, the total time complexity becomes O n plus O n asterisk O log n, which simplifies to O n log n. The space complexity is dominated by the prefix sum array, which requires O n space. Since no other significant memory is used, the overall space complexity also remains O n. This proves that the algorithm achieves the desired balance of efficiency in both time and space. When solving this problem, there are a few common mistakes to watch out for. First, incorrect prefix sum computation is a frequent issue. Remember, the prefix sum array must be calculated iteratively, where each element at index I represents the sum of all elements up to that index in the original array. Skipping this step or making indexing errors can lead to incorrect subarray sums. To avoid this, carefully implement the prefix sum logic and validate it with small test cases. Another common mistake is misunderstanding the constraints. The array must be split into 3 non-empty subarrays, so any split that violates this rule is invalid. Failing to enforce this constraint can lead to overcounting. Additionally, attempting a brute force approach is inefficient for large inputs since it has a time complexity of O n superscript 3. This approach will likely result in a time limit exceeded error for larger datasets. Instead, consider more efficient techniques like two-pointer or binary search methods. Finally, watch out for edge cases. For example, arrays with all zeros or arrays that are too small to split into 3 parts can break your logic if not handled properly. Testing your solution with these edge cases is critical to ensure robustness. Another common issue arises from improper handling of prefix sum ranges. When determining valid ranges for the middle subarray, it's important to use efficient techniques like binary search or two-pointer methods. Without these, it's easy to incorrectly count valid splits or miss some altogether. Tools like Python's bisect module can help efficiently locate valid boundaries for the middle subarray. In interviews, there are certain aspects to prioritize when discussing this problem. Optimization is key. Relying on brute force approaches can be a red flag to interviewers. Instead, focus on demonstrating your ability to optimize using techniques like prefix sums, binary search, or two-pointer methods. Additionally, proactively discussing edge cases during your explanation shows that you understand the problem comprehensively. For instance, you might mention arrays with all zeros or very large inputs and explain how your approach accounts for them. Be ready to discuss trade-offs, such as the space complexity of prefix sums versus the time complexity of binary search. Finally, modular thinking is essential. Break the problem into smaller, manageable components like computing prefix sums, finding valid ranges, and counting splits, and explain how each part fits into the overall solution. This problem has similarities to other problems that involve prefix sums and array manipulation. For example, LeetCode 560, subarray sum equals k, focuses on using prefix sums to count subarrays with a specific sum. Another related problem is LeetCode 1248, count number of nice subarrays, which involves splitting an array and leveraging techniques like prefix sums and two-pointers. LeetCode 1537, get the maximum score, is another variation that requires splitting arrays and optimizing using prefix sums. Additionally, LeetCode 238, product of array except self, involves prefix computations, but it focuses on products instead of sums. These related problems can help strengthen your understanding of how prefix sums and optimization techniques can be applied to a variety of scenarios. When considering alternative approaches, each comes with its own trade-offs. The brute force approach involves iterating over all possible triplets of indices and checking the conditions for valid splits. While this is straightforward to implement, it has a time complexity of O in superscript 3, making it impractical for large inputs. A more efficient option is the two-pointer approach, which uses two pointers to find valid ranges for the middle subarray. This method reduces the complexity to O in superscript 2, making it faster than brute force, though still not optimal for very large datasets. The binary search method, when combined with prefix sums, is even more efficient. By computing prefix sums once, you can use binary search to identify valid ranges for the middle subarray, achieving a time complexity of O n log n. However, this approach requires careful implementation, particularly when handling edge cases. Finally, while a sliding window approach is less intuitive for dividing an array into 3 subarrays, it can be useful in simpler variations of the problem. Each of these methods has its own strengths and weaknesses, so understanding their trade-offs is essential for selecting the best approach depending on the problem constraints and input size. Great job making it through. To wrap up, we've covered an optimal solution leveraging prefix sums and the two-pointer technique. Remember, mastering these concepts can significantly boost your problem-solving skills. Thanks for watching, and don't forget to subscribe for more insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!